All right, welcome to this explainer. Today, we're taking a look at an absolute legend in the electronics world, the BD139 transistor. I mean, if you've ever poked around inside a medium power circuit, an audio amp, or even just a basic motor controller, there's a really high chance you've bumped into this exact component. It's this incredibly versatile, time-tested workhorse that's been powering engineer and hobbyist projects for decades. So today, we're going to completely demystify exactly how it ticks.
Here's our roadmap for today. Number 1, we'll meet the BD139 transistor. 2, we'll look at how it actually works. 3, we'll cover the 3 operating regions. 4, we'll dive into practical applications and pairings. And finally, number 5, we'll talk replacements and safety rules.
Okay, let's dive straight into Section 1, meet the BD139 transistor.
So the BD139 really sits in this perfect medium power sweet spot. It's an NPN bipolar junction transistor, and right off the bat, 2 massive numbers should catch your eye. An 80-volt rating for the collector emitter voltage and 1.5 amps for continuous collector current. That makes it, vastly more capable than your typical tiny small signal transistors. Plus, it handles a maximum power dissipation of 12.5 watts at 25 degrees Celsius, all tucked into a really neat, compact TO-126 package.
Let's get physically oriented here. If you're holding the BD139, looking directly at the front, flat side of that TO-126 package, the pins follow a very strict 1-2-3 layout. Pin 1, over on the far left, is the emitter. Pin 2, dead center, is the collector, and pin 3, on the right, is the base. You'll definitely want to memorize that emitter-collector-base arrangement, but a quick pro tip for you. Always verify this with your specific manufacturer's datasheet. I mean, unless you actually enjoy the smell of burnt silicone, right?
Moving right along to Section 2, how the transistor actually works. Now, as you probably know, with pretty much any NPN transistor, injecting a small base current, which we call IB, unlocks a proportionally much larger collector current, IC. For the BD139, that mathematical ratio, which is the DC current gain, often represented by beta, or HFE, is literally what lets us reliably control hefty loads using super delicate microcontrollers or signal sources. You can just think of it as a highly sensitive current valve.
To put that into perspective, practically speaking, if your control circuit feeds a tiny base current of just 10 milliamps into the transistor, and your specific BD139 happens to have a typical gain of 100, well, you've just unlocked a full amp of collector current. You are essentially bossing around a heavy, demanding load with a mere whisper of a control signal. It's brilliant.
So let's look at Section 3, the 3 operating regions.
Depending on exactly how much current you're feeding into that base valve, you're going to be operating in one of 3 distinct states. First, there's the cutoff region. That means essentially 0 base current, so the transistor is entirely off, completely isolating your load. Next, if you push enough current, you hit saturation. Here, the transistor is fully on, acting almost like a solid piece of wire. And then, sitting right there in the middle is the active region. This is the magical in-between sweet spot, where tiny base fluctuations create perfectly scaled, larger collector fluctuations, which is exactly what we use for signal amplification.
Which brings us nicely to Section 4, practical applications and pairings. When you're using the BD139 as a switch, it's bouncing strictly between those cutoff and saturation states. It's absolutely perfect for driving relays, high-powered LEDs, or small DC motors. But hey, a major word of caution here. Always use a base resistor to limit the current. And if you're driving an inductive load, like a motor or a relay coil, a flyback diode is absolutely non-negotiable. Seriously, unless you want nasty voltage spikes to instantly fry your component when that load switches off, do not skip the diode. Now, if you aren't switching, you're probably amplifying. And in the world of audio amplifiers, the BD139 is very rarely flying solo. It is almost always paired up with its complementary partner, the BD140. See, while the BD139 is an NPN transistor, the BD140 is a PNP transistor. In a complementary push-pull amplifier stage, they act as this perfectly synchronized tag team. The BD139 handles one half of the incoming AC audio waveform, while the BD140 handles the opposite half. Working together, they seamlessly reconstruct and deliver a beautifully amplified, much stronger signal right out to your speakers.
All right, let's wrap things up with Section 5, replacements and safety rules.
Look, when you're repairing a board, there is no magic universal substitute. Reaching for a closely related BD137 or a BD135 might seem super logical, but their voltage limits fall completely short at just 60 and 45 volts. Drop them into an 80-volt circuit and they are going to fail.
hard. On the flip side, something like the MJE340 gives you a massive 300-volt buffer, but it can only handle half an amp of current. And the TIP31C? Forget about a direct drop-in, that's a completely different physical package and pinout entirely. The point is, you cannot blindly swap these out. You absolutely have to perfectly match the operating voltage, current, and package to your circuit's specific needs.
Ultimately, you have to design around the physical realities of the component. Never exceed that 80-volt collector emitter rating. And keep in mind, 1.5 amps is a maximum rating under perfect conditions, not some guarantee that it can just run like that all day long inside a hot enclosed box. It's a transistor, right? Not a space heater? If it's dissipating power, it's going to get hot. So proper thermal design and a good heat sink are absolutely mandatory. And I'll say it again for good measure. Always check the pinout of any replacement component before you start soldering.
So we've walked through its impressive baseline specs, the fundamental mechanics of its current gain, those 3 crucial operating regions, and of course how to safely implement it on the workbench. The BD139 truly is an incredibly versatile, foundational building block in modern electronics. Which leaves me with this one final thought for you. Knowing what you know now about its incredible flexibility, will your next electronics project require a reliable medium power switch? Or maybe an elegant push-pull amplifier? Well, the choice is entirely up to you. Thanks so much for joining me on this explainer, and I hope you feel fully equipped to use this knowledge in your own designs. Catch you next time.